Computer programming is an art because it applies accumulated knowledge to the world, because it requires skill and ingenuity, and especially because it produces objects of beauty. When Donald Knuth wrote those words, he was looking past the cold math of early machines. The problem we face is a massive communication gap, something. You need a highly efficient translator in the middle. That is exactly what Python is designed to be. It thrives on three distinct traits. It is completely free and open source. It demands strict precision, treating uppercase and lowercase letters as entirely separate things. And most importantly, it uses a highly readable syntax that humans can actually parse without needing a degree in computer engineering. So where do you start? Usually, it's right here in the interactive shell. This environment lets you type a single instruction and immediately see the result, making it perfect for quick line-by-line testing. But when you want to build a full application, you move to script mode. This is where you write, save, and execute hundreds or thousands of lines of instructions all at once as a complete program. Python gives you the perfect environment to translate your ideas into software. But a translator can only work with what you give it. You still have to supply the raw materials. This diagram shows how Python categorizes the raw materials of code, known as data types. You have basic numbers. You have booleans, which act as simple true or false switches. You have a special none type to signal the deliberate absence of a value. And you have mappings, like dictionaries, which store linked pairs of data for faster access. You organize these materials by slapping labels on them. Programmers call these custom names identifiers. The only rule is that you cannot use Python's built-in keywords, words like false, class, or return, because the interpreter already has those permanently reserved for its own core functions. These identifiers act as variables, holding your data types. Some of these materials are mutable, meaning you can alter them on the fly. Others are immutable, meaning once they are created, their internal structure cannot be changed. How Python actually manages these physical objects inside the computer's memory is where things get interesting. If you create two separate variables and assign them the exact same number, you might assume you've created two duplicate objects. But if you check their physical location using the built-in ID function, you'll find something else. Python sees the matching values and optimizes the system. It simply points both of your identifiers to the exact same physical address inside the memory vault. This shows that Python isn't just holding abstract concepts in your head. It is actively managing physical resources inside your hardware, making sure every piece of data has a specific, verifiable home in memory. Once your data is in place, you need moving parts to force interaction. We use operators for this. Arithmetic operators handle the math, while relational operators compare two values to see which one is larger or equal. We also use logical operators like and, or, and not to validate conditions, alongside identity operators like is and is not to confirm if two variables point to the exact same object in memory. Combining variables and operators creates an expression. This process takes distinct pieces of data and computes them into a single, unified thought. But think about what happens when you try to calculate an expression using incompatible pieces. Say, adding a whole integer to a decimal float. Usually, the logic breaks. Here, Python steps in with implicit type conversion, automatically coercing the integer into a decimal so the pieces fit. For manual control, you use explicit conversion, typing a command to force a data type to behave exactly how you want. Organizing these data types and expressions is how you establish a stable logic for the machine. It ensures the interpreter understands exactly what to do with the pieces you've provided, creating the foundation for a script the computer can successfully execute. By stacking all these identifiers, data types, and expressions together, you build a complete functioning script. Embedded inside that script, you'll often find hash signs followed by plain English sentences. These are comments. The interpreter ignores them entirely. They exist solely for the human element, to explain the reasoning behind the code to the next person who reads it. That human reasoning is exactly where the entire system is most vulnerable. This is where logical errors will happen. This diagram illustrates why logical errors are uniquely frustrating. The syntax is flawless. The grammar is correct. Because the code is technically sound, the program runs perfectly. It never crashes. Instead, it simply outputs the wrong answer with total confidence. To fix it, you debug. You must trace the program backwards from the bad output, hunting down the exact moment where your logic strayed from reality. Python can bridge the communication gap. It will execute the math and manage the memory flawlessly. But the ability to see a problem, structure a solution, and build it from the ground up, that art form belongs entirely to the programmer.